So today we will discuss about how to achieve this objective of optimal water allocation in thermal power plant with the help of mine bursting algorithm and glowworm optimization technique. Our main objective is to allocate the water supplied to a thermal power plant optimally, maximum utilization under minimum expenditure. Okay, so let us see how it is done. So in this case, you'll require to have a knowledge of glowworm optimization and mine burst algorithm. So both of these are available in my other videos. So kindly go to those videos and see it first. Once you have finished watching them, then return back to this video. And if you have already watched them, then let us continue into the next slide. Okay, so this is the flow chart of this problem. Our objective is our main objective is optimal water allocation in thermal power plant with the help of mine busting algorithm and glowworm optimization technique. So I will just walk through this video, and as you know, this is a part of online internship program conducted by the EnergyinStyle website. And I am the internship coordinator of this program. So here you see, first of all the thermal power plants consist of different units having different functions. So majority of the power plant, thermal power plant, will have these units. One will be the generation unit, from where the power is generated. One is the distribution unit, that means after generation the power is distributed to the national grid or to the other location through transmission cables, or into various sources as per requirement. So that is not part of our work. Our work is to know how to optimally allocate water to every units of thermal power plant such that all the units or the demand of water from all the units is satisfied. Now, in normal cases, this will not be any problem. But when the water supply is reduced or scarce due to some issues, then the decision making is important. Which unit to allocate water, which unit to not allocate water. So here what I will say, let us come back to our discussion that multiple units run a thermal power plant, and each of the units has its own importance to maintain the productivity of the power plant. So like this generation unit, this is very important unit. It houses the steam turbines, and if steam turbines are not rotated, power will not be generated. The steam turbines are connected to the generators, and the generator is used for generating power, which is again supplied to the step-up transformers such that it can be distributed. So without distribution unit, the generated power will not be distributed, and it can only be used for storing. or charging some batteries and all this thing. But majority objective of thermal power plant is to generate power and distribute the same. So, but if you say which one unit has more importance, generation unit or distribution unit, then it is a decision making. So more or less, most of the people who worked in the thermal power plant or who do research on thermal power plant, they will try to say that yes, the generation unit is more important compared to distribution unit. But my argument will be, if it is generated and not utilized, why we are generating this power thing? So each unit has its own importance, and this importance is required to be estimated, approximated, or determined very objectively, very logically, and logically, such that the most important units, its demand is satisfied first, then the next important unit will receive its water, and so on. Then only the water, whatever water is supplied to the power plant, it will be distributed optimally. So let us see, come back to our discussion. This is TPP, generation, distribution. Then we have what? We have cooling towers, we have, right? Then we have, let us say, something known as control panel, we have. And also there are offices, there are staff quarters, and so on. In this generation unit can further divided into steam turbine unit, which houses the steam turbine, and also the generator unit, or the alternator to be more precise, alternator unit. So this can be further subdivided. It is up to you, up to how much subdivision you will do your major units. Now, how to determine the importance of each of these units, right? Cooling tower, control panel, generation unit, distribution unit, offices, staff quarters, and so on. Now let us see, for each unit there are some profit enhancing factors and some loss enhancing factors. That is, profit enhancing factor is those factors which enhance the profitability of a power plant, and loss enhancing factor is those factors which enhance the loss of a power plant. Now let us see the example of profit enhancing factors. One of the main profit enhancing factors, the main product of power plant is power, because power plant sustains by selling power. So this is its main product. So power generation capacity of any unit will be the one of the major profit enhancing factor, followed by the plant capacity factor enhancer. Now power generation capacity is how much power an unit can generate. If it cannot generate any power, then it is zero. If it can generate power, then how much is its potential? I am taking about the potential, not what actually it supplies. Because many times what happens, say one unit has the ability to generate 10 megawatt of power, but it is generating only 8 megawatt. I am not considering this 8 megawatt, I am considering this one, 10 megawatt. Because that is why I am using capacity. Then comes the plant capacity factor. So here plant capacity factor or capacity factor will give us that how much it can generate 10 megawatt, how much it is actually generating, right? And if you multiply 100 with that, then how much it is taking? 0.8 into 100, it is 80%. So this capacity factor will give you how much it is generating compared to how much it can generate. I am talking about, not talking about the interplant, I am talking about the units. Then comes the plant utilization factor. This is also more or less same, but it mainly deals with the utilization part. Then how much employment that unit is generating. Okay, so these are all profit enhancing factor, because the employment we can take it as a positive part of a power plant. This plant efficiency factor, more the utilization, better with the profit. More the plant capacity factor, better with the profit. More the power generation capacity, better with the profit. So all these are positives or beneficiary for a power plant. Now, what are these loss enhancing factors? This loss enhancing factor, rather than referring it as loss, I would say these factors reduce profit. Okay, it reduces profit of a power plant. Example, how much raw material it is consuming, how much power it is consuming or it is required to be consumed, how much impact on environment it has. And by impact I am not saying as positive impact, I am saying about negative impact. How much social impact it is having, this is also negative sense. How much maintenance cost is there in terms of manpower, how many manpower is required to maintain that unit, or this is how many number of labors you require to maintain that unit of power plant, how many technical, non-technical person you require to maintain this unit. So more the requirement of manpower, more will be the cost on the power plant. So it will only contribute towards expenditure. And as you know, income minus expenditure is the profit of any entity, business entity. Right? Now remember, this environmental impact, social impact, all these things are in a negative manner I am considering here. So, like for example, environmental impact, suppose due to this power plant, due to the due to the that ash or gas generated by this power plant, how much environmental impact is there? You know, that is one of the main thing, that is why we are now discouraging any new installation of thermal power plants. We are either shifting towards renewable energy or we are shifting towards natural gas power plant and so on. So this is our environmental impact. This is social impact, means yes, power plant has positive social impact also. It generates employment. But if you consider a unit of a power plant, then that social impact can be negative also, because of that pollution generated by a power plant or a power unit or a unit of a power plant. Lots of health hazard is faced by the local population, also the workers who are working in the power plant. So that thing I am referring to. Then maintenance cost, each unit of a power plant needs some certain maintenance. This maintenance cost is respect to manpower, how many man is required or manpower is required. So this is in terms of manpower and also in terms of monetary, that is money, because not only manpower is required, when you are maintaining some unit, you also require to purchase something. So when you are purchasing, you are expending money, which is only contributing towards your expenditure. And also many regulatory requirement is there, sorry, due to which power plant cannot function in its capacity. So now the major regulatory requirement is from the environmental agencies, and they impose strict regulation on thermal power plants. So that is why what happens is thermal power plant works below capacity, often works below capacity. But remember, all these things that I am talking about is with respect to a single unit of a power plant, like generation unit. How much power generation capacity is there for the generation unit? How much capacity factor it has, this generation unit? Utilization factor enhancement, how much it is doing, enhancing the utilization factor of a power plant. How much enhancing the capacity factor of a power plant. How much power it is generating. How much employment it is generating. All these things are profit enhancing factor. That means it increases the profit of the power plant. Due to this generation unit and its capacity to enhance the plant capacity factor, plant utilization factor, employment, power, the profitability of the power plant is increasing. So that is why we have clubbed all these four parameters as profit enhancing factor. And on the contrary, all this unit has some loss enhancing factor also. So which reduces or forced the profit to be less by contributing towards expenditure, by contributing not allowing the power plant to operate in its capacity, and so on. Okay. So what we have done is we are representing this power generation capacity of each unit of our thermal power plant by P. Capacity factor enhancement CF. Why am I saying this as capacity factor enhancer? Look, the unit of a power plant uh, doesn't have any capacity factor or utilization factor, but it can enhance the capacity factor or utilization factor. Okay, so always remember that I am always talking about that unit, not the entire power plant. Okay. So this loss enhancing factor is also with respect to unit, not with respect to the power plant. So these are all these loss making or loss enhancing factors. These are power enhancing factor. Profit enhancing factor. We are referring profit enhancing factor as PEF and loss enhancing factor as LEF. So this P is power generation capacity, CF is capacity factor enhancer, UF is utilization factor enhancer, employment generator is EG, raw material consumer R, power consumption requirement is PC. Each of the unit has certain amount of or required certain amount of power to run, right? So how much power it must consume to run is represented by this parameter. And remember, this is consumption of power by a unit of within a thermal power plant. So it is an expenditure. Okay, then it is environmental impact E, social impact S, cost due to manpower CM, cost due to monetary terms C dollar, regulatory requirement R subscript, small r. So PEF can be written like this. This M1, M2, M3, M4 are all weightage, or it represents, they are all weightage or it represents the significance of those or significance of importance of all these parameters. They are all known as significance of that unit in enhancing the profit of the entire power plant. Okay. Similarly, you see this N1, N2, N3, N4, N5, N6, N7 is significance of that unit in enhancing loss. Okay. Now, so we have 4 PEF and 7 left. Now remember, you can use many more. You can use or include many other factors also, right? But always remember, they must be either profit enhancing factor or loss enhancing factor. Profit enhancing factor, okay, or loss enhancing factor. Now let us see. You note that these are M1, M1 to M4 is the weightage or significance of that unit. Significance of the, as I say, significance of that unit rather than saying it as unit, let us say it as significance of that parameter or factor in enhancing the profit of the unit. That will be correct. Okay, and this loss for loss enhancing factor, significance of that parameter in enhancing loss of the unit. Okay, so these are significance represented by weightage. These weightage will be within 0 to 1. It cannot be equal to 0 or equal to 1. And these are my design variables, which the value of which I will determine with the help of the optimization problem. That means our objective equation will be maximize y, okay, maximize this y when y is summation of this one actually M1P plus M2CA plus M3UA plus M4EG. This is what in a very mathematical term, summation of all these PEF factor multiplied with their respective significance of weightage or importance, weightage of importance or weightage of significance, whatever way you may say. And then this summation, there will be PEF for each unit and LEF for each unit. So let it be I, let there are I number of units. So there will be I number of PEF, I number of LEF. So let us give each of the unit a weightage of significance, that is MI for PEF, NI for LEF. These MI and NI is not the weightage of significance of the parameters. These are the weightage of significance of the units, big or capital MI and capital NI. But small MI, the small n's from 1 to 4 and small n from 1 to 7 are the weightage of importance of the parameters, not the units. So remember this difference. Now what we have done is, as you know that in optimization problem, there will be a design variable which we change within a constraint, upper bound and lower bound, or lower bound or upper bound, lower limit or upper limit, whatever way you may say. We change those design variables and try to maximize or minimize or try to attain some target values with the help of this objective equation. So this is your objective equation. Y is equal to summation of numerator PEF, denominator LEF for each of the unit. Okay. So this is the objective equation, and I am trying to optimize this objective equation by changing this MI and NI and also by changing this M1, M2, M3, M4, N1, N2, N3, N4, N5, N6, N7. Okay, so we are changing these 4 N's, 7 N, and as many big M or capital M, uh, as many capital M, which is equal to the number of units. If there are, suppose 1, let us take my example, 2, 3, 4, 5, 6. 6 units are there. So there will be 6 big N for pips and 6 big N for lips. So first you sum the pips of each unit and lips of each unit, and then you sum all those, you multiply big M with the corresponding pip of that unit, and then you add the same with the for other unit. So that is what we have done. Okay, so big M represent the significance of unit I multiplied by the pip of unit I, then plus big N, then it will be I minus 1 multiplied by pip of I minus 1, and so on. Similarly for the denominator also. So once you've done that, so what happens is our design variable is then 2 M is design variable, N is design variable, big M is design variable, big N is also design variable. My condition is that they cannot be equal or less than 0 and equal or greater than 1. They cannot be. So this is my constant, both small n and big M, big N. This is my constant. Okay, and this is my objective equation. And optimization technique, or the way I will change this M, N and big N is by with the help of this mind bursting algorithm and glowworm optimization techniques. Both of them generate new positions. So these positions are nothing but the different values of M, N, big N, big N. Okay, then we will enter them into the objective equation and we will compare with the previous version of the objective equation. If it is better, because this is a maximization problem, so if it is more than the previous one, then we will then move ahead in that direction. If it is not, then we will what we do, we will change our direction, but we will follow the system as suggested by the mind busting algorithm and glowworm optimization. You will remember, if you go through my videos on mind busting and glowworm, you will remember that in mind busting and glowworm, both cases they give the position. Mind busting give the position of that mine which will destroy all the other mines of a minefield if some sharp nails are thrown at that mine. So this mind busting algorithm always look for that optimal position. So here the position is replaced by this small m, big N, big N. And in this case, glowworm optimization technique, position of glowworm is considered. So that is what we are saying. By this way, we will optimize, and when this max value is not changing for long term, suppose 100, 200 iteration is gone, but Y is not changing, or Y is not changing, then we will stop the optimization and we will note down the value of this small n, big N to find the optimal water allocation ratio of the power plant. Okay, so how to find it? Let us discuss it in the next slide. Okay, so here lastly, this is the closer. After weightage of the parameters, remember M, N, small one. After weightage of the parameters as well as each unit, this is big one, is estimated by the algorithms, the next step will be to allocate available water of the thermal power plant. Available water means the water supplied to the power plant. Within each unit, strictly as per their PIF by LEF ratio. But remember now the value of M and N is inserted in that first two equation. Okay, where we have multiplied the M's with its corresponding parameters and added. And for N it is the loss making and for M is the profit enhancing. N is loss enhancing, M is profit enhancing for the parameters of each unit. And this is for profit of each unit and this is for loss of each. Now we have to again do another optimization to come to our main object. So what will happen is, let us say that this QP YP. So let us say this YP is the water or amount of water. If let us begin like this, if total amount of water, the total amount of water is Y, big Y, and the amount of water allocated to that each unit, for our example it is 7, is YP, chota YP, okay? Now, before that, this YP is nothing but the ratio of PF by LEF. Yeah, so to be more precise, this is MI into PF divided by NI into LEF. Whereas this PF is, as you know, PF is the summation of MM into the PMs, this parameters, profit enhancing parameters. And the LEF is summation of NN into PN. This PN is actually the loss enhancing factors or parameters, whatever you say, for that unit only. But these are in terms of those parameters, and this YP is in terms of water allocation. Okay, so what happens is that let us say what we will do is that now our next step is I think, okay, so this is the water allocated. So summation of YP is actually this big Y, right? Now, sorry. Now what we'll do is this YP is the water allocated to each unit. Now let us multiply another weightage of significance QP. Small q subscript p multiplied by YP, small yp subscript p. And here p is your number of units, right? This YP is in terms of water allocated. Now, how you have allocated the water? Based on the importance you have received in the earlier optimization. Okay. So, the earlier optimization will give the importance of each of the unit, and accordingly you have allocated the water. Now our aim is that this total amount of water must be utilized optimally, but maximum water has to be utilized. So that is why what we are doing is we are using this term QP. This is another unknown term, and this QP is giving the significance of each of the unit with respect to the water allocated to them. Okay, now you say that what is the difference between this? What is the difference between this one, the way we have determined the importance of each of the unit, and then we have decided that which unit is how much important. Okay, and this one. You know, this one is in term of how each of the unit is contributing towards the profitability of the industry, right? This thing, let us say this is X. This X is a function by which we are enhancing the profit of a power plant, correct? But here in this, the capability of the unit in enhancing the profit of the power plant, there is no relation with the water that has been supplied to that unit. My aim is that the unit which is the most important in enhancing the profit of the power plant, I will supply the maximum amount of water to that unit, followed by the other unit as per its importance in enhancing the profit of the power plant. But the next question arises, how much water? So this answer we are giving in the second optimization, because this is the water allocated initially, and this is the QP which will give the significance of each unit, or take it otherwise, this significance or this QP will show us what should be the optimal ratio of water allocation to each of the unit, which is ultimately will enhance or contribute to the profitability of the power plant. So it is like that there are 10 number of employees, 7 are enhancing profit, 3 are reducing the profit. So if I have some amount of water, I will give water to the employees who are enhancing profit, but I cannot ignore the employees who are not enhancing the profit, because if I do not supply water to them, they will die. That's a very weird example, but it is the case. So we have to supply water to each of the employee, both who are enhancing profit and both who are not enhancing profit, but in such a manner that our profitable employees, or the employees who are increasing our profit, gets a better amount of water, such that they get encouraged and they will work more. That is the more or less the analogy. Okay, that is the more or less the analogy. So here also what we are doing is the unit which is contributing to the profit of the power plant, we are allocating water to that. But how much? That is what we will determine with the help of this optimization, where QP will decide the ratio and YP we already know. So again, QP will be the design variable dV, YP will be the constant, and this QP again same thing will lie between 0 to 1 but cannot be equal to 0 to 1. Okay, and here we have a restriction correct? That all YP will be equal to the total water available or supplied. That is what supplied. And another thing we have utilized is that to magnify the allocation such that it has clarity, because often it happens that suppose there are 10 liters of water and some unit is there where the importance is very fuzzy, more or less same importance. So what will happen is which one to give a higher amount of water, which one to give lower amount of water. Suppose one unit has 7.5 importance, another one has 7.53 importance, another one has 7.56 importance. Which one to give? Only 0.3 is the difference. So in this type of fuzzy cases, a certain amount of magnification is required such the difference of importance between the units is very clear. So that is why we have utilized this exponential function. And as we have to keep in our mind that we cannot just randomly increase this allocation, we have some limit. So this 1 is actually showing that limit. Okay, so 1 minus e to the power qp, that is the weightage of allocation. Let us name it as weightage of water allocation multiplied the amount of water already available. So this is actually constant, you cannot change, but you can change this one. And why this is summation? This is the summation because QP represents the weightage of water for all the P units available there. Or we can also use I, but to make it more clear, I have used P for this. So all the I units, there will be water allocation, and the significance of that units is represented by this Q, which we will determine and which is the design variable. And YP is the magnitude of water already allocated. Okay, so again we will utilize the same two algorithms, GWO and MBA. Q will be that position as I have already explained, and after maximization, so there I have made a mistake. This will not be a maximization, this will be minimization because 1 minus is there, right? And when this will increase, this will actually minimize. And we want a point where actually the remaining y will be 0. This is actually the remaining y. So let us make it as del y. Okay. So y is the total amount of water supplied. So let it be del y, remaining amount of water. So this del y will be the remaining amount of water. So this del y must lead to 0. So it is a minimization problem. And how we are leading it to 0? By using this 1 minus e to the power. This is the magnifier, such that the difference is clear to us. Summation of QP YP. So QP is our weightage of water allocation for P unit. YP is the water already allocated. Correct, for any instance. So this will give you the ratio of water allocation where the maximum water will be utilized, whatever water is supplied, within that maximum water will be utilized, and the unit which is responsible for increasing profitability of a power plant will be entertained more compared to the unit which are contributing to the loss of the power plant, such that the profitable unit get encouraged, But loss-making units are, as they are also essential, they are not tied down. So here it is. This is the video walkthrough of our sixth internship program, where we have used this GWO and NBA two times. First, for determining the importance of each of the unit of a power plant in increasing the profitability of the power plant, and then based on the power plant, how water to be allocated, that golden ratio or optimal ratio we have determined with the help of this equation. This is not max, this is mean, sorry. By using this equation as objective function, QP, the weightage of water allocation, or the ratio of water allocation, whatever way you may say it, QP as design variable, and YP is constant. This YP is actually the water already allocated. You can take any instance as you wish. So with this, I finish this presentation or the video walkthrough of this internship program. So to take part in this internship program is very simple. Complete this assignment, send me the report. I will evaluate it, my team will evaluate it, and once it passes all the quality criteria, we will issue you the certificate of appreciation or certificate of participation. And if you are interested, then that same report will be published in one of the journals of EIS, like International Journal of Hydroclimatic Engineering or Water Resource Management, or any one of the journals we have. So thank you for your patience hearing. Good night.